Hey guys, so we're looking at, still going on with calculus, but this time we bring back in an older topic in with our calculus. So we're looking back at a few things from polynomials. So I did briefly touch on it earlier when we were looking at polynomials, but I did let you know that we do more of it later down the track, which is today. So in blue there is the theorem that we're looking at today. So it says that if you have a factor and it has multiplicity r, then if r is, let's say 2, if you have a factor with multiplicity 2, that means that that factor, when subbed into the original equation and the first derivative, will give you 0. If it has multiplicity of 3, then that factor, when subbed into its original equation, first derivative and second derivative will give you 0. So that's where this r minus 1 comes from. Whatever the multiplicity is, take 1 away, and that's how many derivatives, when you sub that factor into the derivative, you'll get 0. So I've written here in green just some examples of that. So if we have a root that has multiplicity of 3, then when you sub it into the original, the first and the second derivative, you'll get 0. Okay, because following the r minus 1 theorem, when you take 3 minus 1, you get 2, which means you go up to the second derivative. So then same thing, if you have a multiplicity of 4, then you can go up to r minus 1 would be 3, so the third derivative, and they all give you 0. Alright, so in saying that, I've just shown you an example here. Okay, so copy this into your book. The green part there you don't have to write in your book if you feel like that blue part now you can understand it. That was just more for me to explain it to you, but otherwise go ahead if you want to. So this first example, if we have this polynomial, I've just shown you how it works. X minus 3 to the power of 3. So we can see this root of the factor x minus 3, it would have a root of 3, and its multiplicity is 3. Lots of 3's happening there. But what do we know? Well, if its multiplicity is 3, then we can go up to the second derivative. So you can see it here, I've proved it. So when I sub in 3 into that equation there, I get 3 minus 3, which gives me 0 cubed, which is 0. Okay, which makes sense. If it's a factor, it's going to give you 0. So then I differentiate it. It was a chain rule. So I took the 3, times it out the front, subtracted 1 from the power, then multiplied by my derivative. And when I sub 3 into there, I still get 0. And then I did the same thing again. I differentiated my first derivative, which gave me my second derivative. When I did that, a chain rule again. 2 times out the front gives me a 6. Subtract 1 from the power gives me power of 1. And then again, timesing by the derivative, which is just timesing by 1. When I sub 3 into this, I'll still get 0. But watch what happens now if I went to do my third derivative. My third derivative, this time I don't have to do the chain rule, because this is only a power of 1, which means I could just expand this bracket out and get 6x minus 3. So really, I just have to differentiate 6x minus 3, which we know is 6. So there's no way I can, 1, sub 3 into that, and there's no way that that will equal 0, because it equals 6. So that's where the cutoff is, okay? Remember, it's always r minus 1. So that's just a really basic example of how it works. Okay. I wanted to show you one more of how it works and show you the way that a question might use it before we jump into some. So again, you can copy this out in your book if you like, but definitely copy that first example, but this second one, it's up to you. But the question says it wants you to factorize that big ugly polynomial completely. So going back to your polynomials topic, remember whatever the constant is, your factors are factors of that number, okay? Plus or minus that number though. So that's where they said, okay, the positive factors of the constant are 1, 2, 4, and 8, and negative are negative 1, negative 2, negative 4, negative 8. So all the factors, positive and negative. So what do? We start with P of 1, which is what they've started with. They got lucky. When they started with 1, they got 0. Then they went to 2. They got lucky again. So you can see it would be time consuming if you know, it might take you a few goes to get 0. But after they got 2 zeros, now we know here that a power of 5 means it can have up to 5 zeros, 5 roots. So they've got 2 of them. What they've then done is differentiate, because when you differentiate, the equation becomes one less term, which is nicer to sub into. So generally, rather than, testing the other 4, 8, and then your negative values into your original, differentiating as quick as you can, often it's nicer to sub into. So they differentiated their polynomial, and this is the line they got there, and then they subbed in their 1 and 2. They're subbing in their 1 and 2 into the derivative to see if they are repeated roots, because remember, if they're a repeated root, the first derivative will be 0. So what do you know? When they subbed in 1 into the first derivative, they got 0. And when they subbed in 2 into the first derivative, they got 0. So we know that x minus 1 and x minus 2, they are factors. And what we know at least is that they are a power of 2 each, at least. Okay? Because r minus 1, it'll solve into that equation, which will be the first derivative, which we both got. So now let's look. That's 4 roots so far that we know about, which means there's only 1 root left. So why not check to see if one of these are a multiplicity of 3 instead? So they differentiated again. See how it's becoming smaller, the polynomial is smaller to sub into, so it's easier to put it back into more derivatives rather than testing those other numbers. So when they subbed in the 1, they were out of luck. They didn't get 0 this time. So they know that x minus 1 is only a multiplicity of 2. There's no more than that. And when they subbed in 2, though, they struck lucky. They got their final root. So what they knew was x minus 2 has a multiplicity of 3. And there's the 5 roots that they needed. So that means they were done. They didn't have to worry about any other number, anything else, because they found all 5 roots just from the derivatives, which then they know the equation of the polynomial forms that. Okay, so it's a handy tool to have. Sometimes, like that was a pretty lucky question. Sometimes it's not going to get so lucky, where you might have to test a few others and then test their derivatives. Okay. All right. Now, the other way thinking about it is too, if you forgot about derivatives for a second and you just went and plugged all those other numbers in, you'll find very quickly that none of the other numbers gave you 0. Only the 1 and 2 did. Okay, so that's another thing to keep in mind. All right, what I want you to do is have a look at example 3. So it says, consider this polynomial, show that x minus 3 is a double root, and then hence solve the equation. Okay, so pause the video if you'd like to have a go at it. Otherwise, I'm going to jump into my solution very soon. Okay, so to prove it had a double root, well, what does that mean? That means a multiplicity of 2. So if I need to show that this root has a multiplicity of 2, it must be an equal to 0 when you sub it into the original and the first derivative. Okay. You could even test a second derivative there and show that it doesn't, so then you can show that therefore it's not a triple root. But otherwise that's fine. And notice what I've said. I said since p of 3, p dash of 3 all equals 0, then x equals 3 is a double root, and I've even showed them what I know what that means. So now solve the equation. Okay, so a bit of a process there, but through long division I got my answers there. Notice how to eliminate an uglier answer, I divided by my x minus 3 squared, so, and I just expanded that out and divided by that. Okay, so the bigger you can divide it into, the smaller your answer is. Okay. Alright. Okay, so I just thought I'd show you one of the questions I saw in the textbook here. It's a bit of a problem-solving question, a bit ugly, but just shows you how these can get, I guess, a bit harder, but not as common. Anyway, we've got some polynomial. They're not giving us what it is. It has a multiplicity of 4. So we need to show that the derivative has a multiplicity of 3. Okay, now that makes sense, all right, because according to our theorem, that would be the case, but we have to prove it. So all I've done here is written that polynomial out in some way that could be true. we know that some factor has a multiplicity of 4, but we don't know the overall power of this polynomial. It could be a power of 5, which means there's another root there, which is I've represented with q of x, some other polynomial, some other function there that it's timesing by. So because we don't know the overall root of the function, I need to include that there. I can't just assume it's x minus a to the power of 4, it being the only a root of 4 could be higher. So whatever q of x is. All right, so what we need to do is we need to differentiate, okay, because that's what we need to show, that it has a multiplicity of 3. So if I had to differentiate, remember, this has an x in it, and this, whatever the q of x is, also could have an x in it. When we have to differentiate a polynomial where there's an x and they're timesing together, what do? Hopefully someone thought or said out loud the word product rule. So p dash of x, and it's not going to be pretty, vu dash plus uv dash. Let's call this one u and this one v. So u is equal to x minus a to the power of 4. And v is equal to q of x, whatever that is. Alright, so if I differentiate u, it's a chain rule, so 4 out the front, x minus a, power of 3, timesing by the derivative of the brackets, which is timesing by 1, which will make no difference. V dash, this one's interesting. I don't know what q of x is, but I know that when I differentiate it, I'll get q dash of x, whatever that might be. Could be 0, could be the number 1, could be anything. So, putting it into my formula, this is what I get. So this is what I get. When I clean this up, I could bring out, let's see, 3 of my x minus a's. Okay, so now in brackets, what I'm left with is 4 timesing by q of x, plusing with an x minus a that's timesing by some other function, which means that that will be affected by whatever q dash of x is. Okay, and let's have a look. What do we have? We have x minus a to the power of 3 out the front. Because remember, this, all of this out the back there is just some function, okay? Something else. We don't know what it is, but what matters to us is that we just proved that that original factor that had a multiplicity of 4 will now have a multiplicity of 3. And what I can do is let that big ugly function, whatever it is they're adding on, be just some other polynomial. So there we've proved that the first derivative has a multiplicity of 3. So you could do that exact same process again, that exact same proof, do the product rule again, if we had to then show that the second derivative had a multiplicity of 2. The exact same thing would happen. Okay, so exercise for today, I'd like you to have a look at exercise 8.13. So I'll write it up the top here. So we're on exercise 8.13. I'd like you to have a go at questions. Let's go all. There's only 9 questions in the exercise, and I think it would be worthwhile. Okay, see how you go with that, and I'll see you guys on our next lesson.